G'day everyone. So the last thing we want to do in scattering is talk about low energy scattering and resonances. We now have all the tools that we need to understand what happens here. So for concreteness, I'm going to start with a square well potential. Now this is really just a convenience at this point. The specific mathematics will depend on the particular potential, but the general ideas that we're going to come across will work for many kinds of potentials. In this case, we've chosen an attractive square well potential. The fact that it's attractive will be a key ingredient to what comes later when we talk about resonances. So here we've just defined kappa and k in the usual way, where these are going to be the coefficients that come into our wave functions. Now I'm going to assume that you guys know how to solve the Schrödinger equation, write down and solve the Schrödinger equation by now for this simple problem. So the solutions are going to be inside, it's just going to be a times the spherical Bessel function of the first kind, kappa r. This is for r much less than, r less than a. This is for r less than a. And outside, we need a wave vector k instead of kappa, and we also need to include the spherical Bessel function of the second kind. When we're inside, we don't need to include the spherical Bessel function of the second kind because that one diverges as r tends towards 0, or as kappa r tends towards 0. But outside, we're never going to have that problem because we never get to 0. Now we impose the boundary condition of analytic continuity at r equals a to get the relationship between b, c, and a. Analytic continuity is where you take the derivative of the function over the function at the boundary condition. This is just to get rid of the overall normalization factors inside and outside. So inside we simply have the derivative of the Bessel function over the Bessel function itself, with the wave vector kappa because we're inside the well. And coming from outside the well, we'll have, worth noting here that the derivatives are taken with respect to the full argument. Okay, so this gives us a relationship between b and c, and now what we need to do is think about what's happening at large distances where we know the wave function. So at large distances, we can expand this r by taking the large distance limit of the spherical Bessel functions in the standard way. So they're the leading terms of the spherical Bessel functions for large argument kr. Now we want to make a connection with the phase shifts that we had defined previously. And previously we wrote, which we can now expand. And I'm using here the sine rule, sine a plus b, where a is kr minus l pi over 2 and b is delta l. And now if I compare this equation with this equation, I can express this ratio b over c in terms of the delta. Now I'm going to spare you the gory details, but if I combine this equation with this equation up here that I wrote earlier, then I can put those together and I can obtain like I said, I'll spare you the gory details. The interesting thing that we're pulling out here is, firstly, I'm only doing this in the limit that Ka is much smaller than L plus 1, although that's not quite the same as Ka is much less than 1. And In fact, we've gotten something which seems fairly reasonable. This part here, the Ka to the 2L plus 1, is the usual limit that we obtained earlier for low K. This part here is a very complicated function, but it's only a function of the well properties itself, kappa, A, etc. So in this case, there's only two well parameters, the depth and the width. And kappa here, because we're at low energy, kappa is very close to square root of 2mv over h bar. So this gives us some typical behaviors that we can extrapolate. So the first thing to note is that for large L, tan of delta L is going to drop very fast. In fact, it turns out it drops faster than e to the minus L. And so that means that we get some cutoff at L max, just pretty much in line with what we expected. And the second thing is that for Ka tending towards 0, then tan delta L is going to go as Ka to the power of 2L plus 1. This is a very generic feature of scattering in general. And so this is a useful feature for us to know as we go forward. So for L equals 0, we have 2L plus 1 over 2L plus 1 double factorial is equal to 1. We've got Ka to the power of 2L plus 1, which is just Ka. And we have this rather complicated function, which turns out to be... Now remember that this specific function here is very much a function of the fact that this is a square well. If it was a different shaped well, it would have a different function here. But we can push on with this tan because it's going to give us generic features, which would be true for any attractive potential. So we have our particular form for the scattering phase shift delta naught. And now what we're going to do is we're going to keep K small in our experiment. So we're going to do lots of low energy scattering, but we're slowly going to increase the well depth. So imagine that we're doing this experiment. We're keeping our beam at low energy, but we're slowly increasing the well depth while keeping the experiment running. So because the well depth increases, kappa is also increasing as the square root of the well depth. Now we keep increasing the well depth until we get to kappa A is equal to pi on 2. Now what happens? That means that tan of kappa A is going to infinity. And that means that tan of delta naught is also going to infinity. So what's happened? It turns out that at kappa A equals pi on 2, a bound state has appeared in the well. Now this is where it's a big advantage to have chosen a simple well shape like the square well. So let's quickly remind ourselves of what bound states in square wells look like. So that's the potential. And our bound state inside it will look something like we call our wave function u of r. Now we're only interested in L equals 0 S wave functions. So the Schrödinger equation is going to be, so now we've actually got it back down to effectively a one-dimensional problem. So the solutions to this are, and now kappa and K naught have been defined as before, but K naught is a positive integer here so that we have an exponential decay. Sorry, positive number here so that we still have an exponential decay as r goes to infinity. And then analytic continuity will give us the ratio of A and B. So that's the derivative of the interior function divided by the function inside at the boundary. And for the exterior function, we get... This has a solution when... And kappa here is square root 2m of E plus V naught, where E is the bound state energy, and kappa naught is K naught is square root of 2m absolute value of E. So to have a bound state, we require that tan of kappa A is less than 0 from this requirement, and so that means that we need to have kappa A greater than around pi over 2. Otherwise it's not going to be negative. So this is a little aside to remind us of when a bound state will appear in the three-dimensional square well. So back to our problem, our scattering problem, we have found that tan of delta naught can get very, very large for low energy scattering if the well has a particular depth and width corresponding to a low energy bound state. But we've also found, conversely, that for low energy scattering, tan of delta L is going to go as Ka to the power of 2L plus 1, where Ka is a small number. So this is small. These two results are in tension with each other. How can we resolve this? The way that we can resolve this is by including a denominator which depends on the relative position of the bound state. So we have this tan of delta is equal to minus gamma over 2 divided by E minus E naught. The factor of 2, of course, is just definition, and we're going to take the gamma as being proportional to Ka to the 2L plus 1, and the energy denominator is where we're going to be able to get that infinity in tan delta when we expect it to be there. So when we have the resonance, E and E naught close to each other, this thing can get very, very large. Now generally there'll be some additional background as well, which will depend on K, but this is kind of a technical aspect. So generally you'd have that the full delta L as a function of K would be some background phase which really doesn't change too much with K, at least in the vicinity of E close to the resonance. And then you've got the fast changing part here, fast changing resonant contribution, which causes most of the disturbance in the vicinity of E naught. But we can ignore this technical aspect for the time being. So now that we know what our phase shift is doing, we can look at what happens to the scattering amplitude. Now there exists an expansion of exponentials in terms of tans, and it looks like this, which is useful for us. Where in that last step, I replaced tan delta with this formula here. This is the famous Breit-Wigner formula. It tells us what's happening to the scattering amplitude in the presence of resonances. We can also then ask what happens to the partial cross-section. And we see straight away that this is a familiar Lorentzian form. It's a resonance formula. So if I am passing my beam energy close to the resonance energy here, then I will approach the unitarity limit and then come down on the other side. And the width of this peak, which is not drawn very well, apologies, is something like gamma, which is proportional to Ka to the power of 2L plus 1, but has a finite width. So if you're right on resonance, you're at the unitarity limit because this part here is going to go to 1. And then if you're a little bit outside of that, it drops away as 1 over energy squared. Similarly, we can draw the phase shift itself as a function of energy. Let me put a little minus here just to get rid of that minus sign. And we're going to get something like a tan function, inverse tan function, I should say. So when we're at resonance, tan of delta L is going to infinity, so delta L is pi on 2, and then it's sort of a smoothly varying function between 0 and pi on either side of the resonance. So when the resonance condition is met, the cross-section can be as large as the unitarity limit, and note that that unitarity limit up here is much, much larger than the geometrical area a squared. One more point is that this phase shift is often seen in experiments. So when you go from E0 minus gamma to E0 plus gamma, you're making a phase shift of approximately pi. So that's talking about low energy scattering and resonances. But now consider a Ka which is just smaller than pi on 2. That's going to lead us to something called the virtual level. The nature of the scattering is still going to be resonant, but there's no bound state yet. We're still going to have this resonant shape in our scattering cross-section. We're still going to have this step of pi in the phase shift, but there's no bound state yet. This thing is called a virtual level. So the virtual level is the not quite bound state that still causes a resonance in the scattering cross-section. A final interesting point is to look at the S matrix near the resonance. So what happens at resonance is that there is a pole in the scattering matrix. What does that look like? Well, now we have to think about the energy space being extended into the complex plane. So this is the real part of the energy, and this is the imaginary part of the energy in the usual way. And now we have some resonance which is sitting off this real axis by a little bit. By a little factor, gamma over 2. Alternatively, we could think about in K space. In K space, so we have a pole either in K space or in energy space. What does it mean to have a complex energy pole? So consider, if you will, a quasi-bound system. This is energy versus R. And let's say we have some potential that looks something like this. This is U of R. That means that there are going to be bound states like this. And there'll be some sort of quasi-bound states. In this potential, the bound states with E greater than 0, these quasi-bound states, they can escape eventually, but they may take a long time to do so because they have to tunnel through this barrier here. So they can get out, but it could take a really long time. So if we think about these quasi-bound states and we normalize them so that we have something like the integral from 0 to the A, some, let's say A here, some part inside the barrier. This is approximately equal to 1 because we can normalize these states as if they were properly bound. Of course, they're not perfectly bound. And then if we think about the time evolution of these quasi-bound states, I could write something like this. Now if I expand this ER using the formula that I had up here, E0 minus I gamma over 2, then I will say that this is equal to that's my normal phase, but I also pick up some real component here, which depends on time. And this is an exponential decay of the wave function. So the probability that the particle will remain bound, in other words, the probability to be found inside the well, will be the integral and that's going to be proportional to e to the minus gamma t over h bar. In other words, it has some finite lifetime. The bound state will decay out of through the barrier. The quasi-bound state will decay through the barrier with a lifetime of h bar over gamma. So that's what we mean by taking the energy pole off of the real axis. It means that we are dealing with a quasi-bound state or a virtual state. Well, this is probably a good place to stop, and we've discussed a lot of stuff about resonances and quasi-bound states and the Breit-Wigner formula, which has huge importance for many kinds of scattering, but this is also a good place to stop. So thanks very much for listening, and I'll see you later.